Today I'm going to tell you a story that begins with a mistake and ends up being a really interesting exercise. Let's take a look at the function 1 over x, and this is just an example because I could do this with any function, but I want to look at 1 over x and actually just on the right side of 1 over x, which is why I chose to write it like this: 1 over the square root times the square root, because then, because of domain restrictions, we don't have the left side. Okay, so the mistake that I was talking about happens when we first try to learn graphic transformations of functions. So vertical translations and horizontal translations. I find it very common for people to understand the concept of a vertical translation, but still have difficulty drawing the functions. And I could say the same thing for horizontal translation, which is this purple one here. I think that this is entirely understandable because this graph looks very strange. You want to think that you're taking the black function and pulling it down a little bit to make the green function, but then clearly there is something strange happening over here where they look like they are in exactly the same place, like they haven't moved at all. But this part looks easy. This part looks like it has gone down by 1 unit. And if you've already thought about this quite a bit, then you know that there's nothing wrong with the picture. It just looks wrong, but it's not wrong. As you move left and right along the function here, what you want is for those 2 points, one in each curve, to always have 1 unit as a vertical distance between them. And they do. Like even here, you see the distance remains as 1 unit. The reason why you don't see it moving as much here as you do here is because of the derivative. The derivative is bigger in this part, so the function is going down a lot faster. So it doesn't take that long for it to go down by 1 unit. And that's kind of what makes it look like the translated version of it is not in a different place at all. And of course, I could say the exact same thing about the horizontal translation, right? Where the derivative is very small, it goes down really, really slowly, so I can go to the right by 1 unit without moving vertically almost at all, which is what makes it look like it's in the same place. And that's why I chose 1 over x as an example for this, because then it's really symmetric and you can see the exact same thing happening in the vertical translation and in the horizontal translation. So when I said that the story begins with a mistake, the mistake that I'm referring to is take the function 1 over x, print this on a piece of paper, and try to draw it. Try to draw a vertical translation and a horizontal translation by hand, and people inevitably draw it wrong in the beginning when they're just learning this topic. They draw it wrong because they haven't had that much time to think about the subtleties of the big derivative and the small derivative that we were just talking about. So they kind of want a translation of 1 unit to mean that the new function is going to be, in a sense, 1 unit away from the original function. They end up drawing something that looks like this, which is neither a vertical translation nor a horizontal translation. If you try to look at it as an attempt at a vertical translation, you will see that even the domain of the function is wrong, because the domain of that side of 1 over x is just from 0 to infinity, and the red function has a domain that it's starting at -1, so it's very wrong. And on the other hand, if you try to look at it as an attempt at a horizontal translation, which would in fact change the domain, then the range of the function is wrong, because if you were taking the black function and translating it 1 unit to the left, of course the domain that used to start at 0 is now going to start at -1, and that is happening in the picture. But that wouldn't change the range, and the range of the black function starts at 0, the range of the red function starts at -1, so it's wrong either way you look at it. Okay, so that was the beginning of the story, the mistake. What is the interesting exercise now? I wonder how I can actually draw this function that is not a translation on any particular direction, but the description of that red curve is more like it's always 1 unit away from the original function. And we're going to have to think a lot during this exercise about what it means to be always 1 unit away, because clearly each point in the red function is a certain distance from each point in the black function. There's a lot of distances that we are talking about here. But in a sort of intuitive sense, you can see that the distance between those two curves remains constant at 1 unit. But before you say, and this is a comment that I hear a lot about this, that I should just do both translations and I would get that same effect. First of all, that's wrong, okay? If I just take the black function 1 over x, translate it down by 1 unit and left by 1 unit, I get the blue curve, which is not the same as the red curve. In many parts, like up here or way off to the right here, it does have kind of the same distance to the black curve, but around here, at the place where it turns the corner, you can see that it doesn't have distance 1 because the black curve goes through the point 1, 1. The blue curve goes through the point 0, 0. The distance between those 2 points is not 1, it is the square root of 2. And again, it's not yet very clearly defined why it's those 2 points that should have distance 1. But it is, and the red curve is the curve that does that. And the other objection that I have to this suggestion of just doing both translations is that it feels very specific to the function 1 over x. And of course, I am going to want to do this with many other functions later on. Okay, so here's what we're going to do. We have the function y equals 1 over x, and we have this other curve that we want to draw 1 unit away from the original curve. And the problem is that for any point in this curve and any point on the other curve, they have a distance, which will be different if I choose a different point, but that's not the 1 unit I'm talking about. I want this distance here to be equal to 1. So there is a correct point to take on the other curve for each point of the original curve. And this is very similar to what happens when we are asking about the distance between two parallel lines, because the same thing is happening here. A point on this line, a point on the other line, they have a distance here between the 2 points, but clearly that's not what we mean by the distance between the 2 lines. We're talking about the perpendicular distance between the 2 lines. So if I take this point on this line and I want to find what the point on the other line is to correspond to this one, I need to find a line that is perpendicular to this one. And in the case of lines specifically, this is equivalent to saying that when I say the distance between the 2 lines, I mean the shortest possible distance between any point on this line and any point on that line. This is the shortest one. That's only going to happen for parallel lines, because if the lines have an intersection, then the shortest distance between them is 0 at that pair of points. But in the case of curves, I don't really want to say this thing about the shortest distance, because I don't think this will happen for this curve. But since they are curved, it is possible that they will have an intersection somewhere else. An example like this, for instance, if I want to start with this distance here being 1 and keep the distance as 1 as I follow along the curve, then it's going to cross here. But that's irrelevant to the problem that I'm trying to solve, because I'm trying to keep this distance as 1, this distance as 1, and then for this point, I want the distance 1 to this other point here. That one is irrelevant. So I don't want to talk about the shortest distance between the curves as a whole, but only about the distances locally at each point. So the perpendicular thing is exactly the same as we're going to do here. I need this thing to be perpendicular and that thing to be perpendicular as well. But the problem is that those are curves, they are not lines. So initially it doesn't make as much sense to talk about something being perpendicular to a curve. Well, I'm going to handle this issue in exactly the usual way, which is to say that what I actually mean by being perpendicular to the curve is that this distance segment here is actually perpendicular to the tangent lines of the curves. And now everything is making sense. I have 2 tangent lines that are parallel to each other, and I just have to calculate the tangent lines. But be careful, because first of all, they are not tangent lines to the same function. One is on the black function and the other is on the red one. And also, they are not tangent lines, not even for the same value of x on two different functions. The blue line is tangent to the black function at this value of x, and the pink line is tangent to the red curve on this value of x. If we were solving correctly the original problem of just doing a vertical translation, then you would also get parallel lines, because vertically translating doesn't change the slope of the tangent lines, but they would be tangent to the different functions at the same value of x. This is simpler than the situation that I'm studying right now. Okay, so I'm not actually going to need the pink line. I took it out of the picture. And any point in the black curve can be called x and 1 over x, because that's the function whose graph I'm looking at. And of course, the fact that the derivative of 1 over x is negative 1 over x squared is going to be relevant here, because it is the slope of this tangent line. But the trick here is going to be that I don't actually want to think about just the slope of this tangent line. I want to think of it as a line. I want to give it an equation. And because the value of x of the other points that I'm going towards is not the same value of x as the original point, then I want to think of this whole thing as parametric curves. And for this reason, I am changing the variable x here in the name of the point to be t instead of x, because that's going to make it less confusing when I get to the final answer of the coordinates of the other point, in which the x coordinate is not going to be x. It's going to be some expression involving t. But the direction vector of the blue line is then 1 and negative 1 over t squared. And you can think of this as you've taken the derivative of each coordinate of the curve separately, or you can just think in terms of slope, and this over this is the slope of this line. It doesn't matter. You're going to get to the same result in the end, because the original curve that I'm dealing with happens to be a function. But the thing about taking the derivative of each coordinate is a little bit more general, because then you can do this same thing for curves that are not functions in the beginning, if you want to do that. This is just the direction vector. If you wanted to write the whole equation of the line, it would be this point plus a parameter times this vector. But you don't need to do that right now, because all that I want is to find a perpendicular line to this one. And for that, I have a perpendicular vector, which I have called w, which needs to be perpendicular to this vector right here. So if you're still thinking about these two lines, the blue one and the orange one, in terms of slope, then you're not going to change the first coordinate of the direction vector of the orange. It's just going to be 1. And the slope of the orange line is going to be minus 1 over the slope of the blue line, which was this. So the slope of the orange one is t squared, which is written here in general for a vector of slope a. But since we're not necessarily really thinking about lines as linear functions as the slope-intercept form, there is a different way that you could do this as well, which is to change the coordinates and reverse the sign of one of them. Obviously, it's not going to be a different normal direction. It's just two different ways of looking at the same thing, because this vector is a multiple of that one. So you're choosing the same perpendicular direction, of course, because there's only one perpendicular direction there, but you're choosing different vectors on that direction. It's a multiplication by negative a from the orange to the green. So they are the same vector, and both of them are equally good for this exercise. And in fact, for this particular example, I chose the orange one instead of the green one, because the slope was already a fraction, so it just looks a lot prettier if I do it this way. But I do want to mention that the green one is better for the general case, for when you want to do the same thing with different functions later on. And the reason is that sometimes the slope is going to be 0. The function in my example is the function 1 over x doesn't have any turning points. But if you're doing it for a function that has turning points, then the vector v is going to be a horizontal vector, a is 0, and then you don't want to divide by 0 here. What you want is for the perpendicular vector to v to be the vector w, which is vertical, and then it is the vector 0, 1. So that's going to be relevant later on when I do the general case. I will use the green one, but for now, for this example, I'm going to stick with the orange one. Okay, so what I need to do right now to find a point over here that is going to be part of the red curve that I am looking for, what I need to do is to start from this point and to move 1 unit in the direction of this vector here. I mean, it's actually -1 unit because I am moving to the left for this very specific example. But of course, in a minute, this is going to be a parameter that we get to change as we want. So in order to move exactly 1 unit in that direction, or exactly a specified amount of units, I need to know the length of the vector itself, because that depends on t. So that's going to change as you walk along the original curve. And just using Pythagoras, the length is that. I'm going to simplify it by rewriting as the square root of 1 plus t to the power of 4. And now this point P here that I am looking for, like we were mentioning here, it starts at the original point and then subtracts 1 over that length in the direction of the orange vector. That's the answer. You might want to write that down to compare when we go back to the computer screen with what I'm going to type over there. But I wanted to point out that I mentioned a while ago that I was changing the coordinate from x to t, because when I finished the calculation, the first coordinate of the points on the red curve were not going to be x. They're just a complicated function of t. So if you wanted to write the red curve as y is a function of x, instead of just the parametric equation of a curve, you would need for this to be x and then the other coordinate to be y. In theory, you can do this by writing this and solving for t, because then you'll get t in terms of x and then substitute into the other t over there to get y in terms of x. But that's just in theory, because this really doesn't look like an equation that I want to solve. And even if I did solve it, it wouldn't be very helpful in the long run, because remember, y equals 1 over x is just an example that I'm doing. This is not the whole extent of the problem. I want to be able to do this for any function. And it's always going to be a complicated thing here. So even if for this simple example, it turns out to be a simple enough equation that we can actually solve, there's no guarantee that for any other function, for any other example, this is going to be something doable. So I'm not even going to touch that. What I am going to do is to go back and do the whole thing over again in general. So that black thing over there is a little bit of a curve, the graph of a function f of x. So the highlighted point there is t and f of t. It has a tangent line with direction vector 1 and f prime of t. Perpendicular to that is a vector negative f prime t and 1, where, like I mentioned before, I did not do the 1 over slope thing because the slope might be 0 sometimes. This is the length of the vector, and now I want to move k units from the original point in the direction of that vector. I have also mentioned this before, that although my original example was 1 unit specifically, I want to do it a little bit more general and ask for k units. So here's just writing that down. The point P is the original point, plus this much in the direction of the orange vector. And if you want to put together the coordinates, it looks like this. Now let's go back to the computer. So the part that I was hiding from you before is that the way that I typed this red function in GeoGebra was exactly what I've just showed you. And an interesting thing to point out here is that even though this has to be given as a parametric curve, because I can't isolate x in terms of t, even though I can't do that, the picture that I am looking at, the red curve, is still a function. it's a function because it passes the vertical line test. And I find it important to say that because a lot of times people feel that the definition of function should somehow involve the expression of a function, as in the function needs to be something that I can write down in terms of x squared and square root of x and other stuff of x. And it really doesn't have to be. In this particular case, it probably can be done because it's a polynomial of degree 4, which is solvable, but we really don't want to do it. But you can imagine that just making the function, the original function, a little bit more complicated would already turn this into an equation that you really cannot solve. So there really is not going to be a expression for the function that you are seeing, the result of the question, find the function that is 1 unit away from the original one. There is not going to be an expression, but it can still be a function because the definition of function is not that it has an expression. It is that it passes the vertical line test. And this other one, I've typed the whole thing again, but in a much more generic way. As you can see, the curve down here, I am using f of t and p of t, where f is my function 1 over x, and p I've defined to be its derivative. So I'm doing that instead of typing the actual functions that they are, because I plan to take this out of here and put a different function in its place and have the whole thing work automatically. I've also added a slider here called k. Now it has k equals 1, which is going to be the distance between the original curve and the new curve that I want to draw. And of course, when it goes negative, it means that it goes to the other side of the function. So we can see that part working first. We get farther away, we get closer. Now k is negative, we go to the other side. And as k gets bigger, you can see something very strange happening. You probably didn't expect to see this kind of behavior in our function, and it definitely looks wrong. However, it is not wrong. It's just really strange because the thing is that I'm looking for a lot more units of distance now, 3.6 units, and this place around here where it's doing this sharp curve, it's kind of like it doesn't really have 3.6 units to fit in there. So you can see that the distance is correct here, here, here. Of course, I'm doing this by eye, so I'm not being very precise, but you can believe me, right? Most of these distances that I'm drawing are correct. They are perpendicular to the function, so they are normal lines. But when it gets around here, the normal line is going that way, and that's just the distance that it wants to have. The normal line here goes that way, and this is the distance. So there is nothing wrong. This is actually what the curve looks like. It's just not going to be very pretty unless k is small enough. But now we can try to see this with other curves. For example, let's try sine of x. Look, that is very pretty. It also does the strange behavior up here when it gets farther from the sine. And when k is negative, it does the same thing on the bottom. So I don't know, you can try this with any function. Let's do x squared e to the power of x, any function that you want. So I hope you've enjoyed this exercise. It began, like I said, from a mistake that people do in drawing, but here we can turn the mistake into the correct answer by changing the question, right? It was the wrong answer for the question of translation, but it was a correct and very interesting answer to this new question of drawing a curve that is 1 unit away from an original curve.